Hey guys, what's up? Mr. Brotherton here. I'm going to be talking about the properties of water. So this is the second lecture about the chemistry of life, and this one is about water. Alright, so the really important thing to know about water is that it is a polar molecule. Okay? I know I asked you guys, if you were an astrobiologist looking for life on another planet, what would you look for? The number one thing you all said is water. But why? Why is water so fundamental, so important to life that it's the number one thing you would look for? Okay, not a lot of you knew. Today we're going to kind of dig into that. The biggest thing is, it is polar. We'll find out what that means here in a second. So why are we studying water? All life that we know occurs in water, both inside and outside of the cell. So if you look here, here's all these different parts of a cell, right? All of these things that you learn about, a mitochondrion and your nucleus and your Golgi apparatus and lysosomes and all of this stuff. But what we really never talk about is the fact that all of this blue stuff, okay, the cytosol or cytoplasm, that's all essentially water. So 75 to 85% of all cells are just water. Why is that? Why is water so important? And it goes back to its polarity. So, fundamentally, the chemistry of water is the fact that the oxygen in water has a higher electronegativity than the hydrogen in water. That means that the oxygen in water is going to be stealing more, or it's going to be stealing the electrons for more of the time from the hydrogen, and the hydrogen is going to be left out there like, man, I wish I had my electrons, but I guess I'll let oxygen have them more because he really wants them a lot more. All right, and that's going to give us a very polar molecule. Polarity means, just like a magnet, one side is going to be positively charged, one side is going to be negatively charged. So if we look at water, that gives us something really cool. All right, our oxygen becomes negative, our hydrogen becomes positive, and then you end up with this. This little symbol means delta, which is a change. So this side becomes delta positive, this side becomes delta negative. So our oxygen is negative, our hydrogen becomes positive, and then you start to get these really interesting weak bonds between your hydrogen on this water molecule and your oxygen on this water molecule. And we call that little weak attraction a hydrogen bond. Now, these things don't last very long. Each hydrogen bond is probably only lasting for about a trillionth of a second, all right? But the collective power of all of these transient hydrogen bonds gives water incredibly awesome properties that are conducive to life, all right? So only a trillionth of a second here, but if you look, each hydrogen or each water molecule is going to be bonded to a couple of its buddies around because of this weak attraction. So that's going to make water a very sticky molecule. That stickiness, that polarity, gives us a couple of really interesting properties. The first one is going to be cohesion and adhesion. So cohesion is the attraction of water to itself. Co means together, so all of the water hanging out together is cohesive. Whereas adhesion, okay, think addition or adhere to, so that's sticking to something else. So water, when it sticks to something else, it's going to be adhesive. All right, so those hydrogen bonds and that partial charge on both the hydrogen and the oxygen can allow it to also stick to other things. And when those two sticky properties, both cohesion and adhesion, come together, we call that capillary action, all right? And that's how our trees are going to work to get water to the top of our trees. Another thing, more things can dissolve in water than any other known substance in our universe. Okay, it is a good solvent. The reason for that is because it has both a positive part of it, so it can attract negative ions to it, and it also has a positive part, or it has a negative part to it, sorry, so it can attract positive ions to it. All right, so that gives it both the ability to attract hydrophilic things, so that's things with a charge like water, and then it can also repel hydrophobic things, so that would be things that don't have a charge, and that is what allows really interesting chemistry to happen inside of life, that battle between hydrophilic molecules and hydrophobic molecules. Another really cool thing is it has a lower density as a solid. We'll get into that. It has a high specific heat. We will also get into that. And it has a high heat of vaporization. All of these things make water extremely important to life. So let's dive in a little bit. All right, cohesion and adhesion. We talked about that. That is the bond between your H2O molecules. It makes water sticky. So that gives you things like surface tension. When you see something like a water strider hanging out on top of water, that's surface tension. And it can do that because water sticks to itself. Adhesion is going to be the bond to other things. And that gives us things like capillary action, and when in chemistry you observe the meniscus. All right, so let me pop up these pictures here. So right here you have adhesion. So on the side here it's adhering to this glass, so the water's sticking to this glass. And up here you have water sticking to itself, so that way our little water strider here does not fall through. And then here once again you have capillary action. This kid is able to suck up this milk from the straw. Milk is mostly water, because of that stickiness of water. So how does water get to the top of the trees? Well, it has to do with transpiration. So you heat up the leaves at the top of trees, and what happens is water molecules start to get pulled by that heat. They start to evaporate and rise, but they're in these chains. They're all stuck to each other in these chains of hydrogen molecules, so it starts pulling more up and pulling more up and pulling more up. All right? So water is the solvent of life. This is extremely important. This is probably the most important thing to know about water, is that chemical reactions can take place, and water can catalyze reactions because different things get attracted to the different charges in water. So a solvent is going to, hold on, sorry, let me back up here for a second. So solvents dissolve solutes, and that makes solutions. So a solvent in this case would be water. That's the thing that's doing the dissolving. A solute, in this case we're looking at salt, okay, would be our solute. And then when salt mixes with water, you get salt water, and we call that a solution. So if you look here, what you can kind of see happening is you have this negatively charged part of water, which is oxygen, and you have this positively charged part. So when it comes in contact with ionically bonded salt, it can disassociate those bonds, because remember, an ionic bond is not that strong, all right? And what you get is this sodium disassociating from the chlorine and then orienting itself like this with a ring of oxygens around it from the water. And then here you can see this negatively charged chlorine now gets a ring of positively charged hydrogens around that. So that's just one simple example of what water does with lots of different solutes, and that's why it's so important for life. All right, so what dissolves in water? Well, anything that is going to have a charge. So anything that is polar is going to dissolve in water. So this proteins tend to not have charges, so they don't really dissolve in water, but something like a carbohydrate, so sugar, is going to have a charge, and it is going to disassociate in water. So once again, we have this here. You can see what's happening here. You have a positive ion, so these oxygens kind of surround it. Here you have a negative ion, so our hydrogens kind of start to surround it. All right, what doesn't dissolve in water? Anything that is hydrophobic. So if you pour oil into water, they separate, they do not mix well, and that simply is because you have these long chains of hydrocarbons, all right, that are not charged. Therefore, they don't really care that oxygen is negative and the hydrogen is positive. It doesn't matter to them, all right, because they are not charged themselves, so it doesn't really affect what they're doing. So ice is extremely interesting. Most solids sink. This is something we just take for granted, right? You're like, okay, ice floats, whatever, who cares? But what's really cool about that is the fact that when water gets cold, those hydrogen bonds that I said earlier that are breaking about every trillionth of a second, what happens is they start to crystallize, and usually each water molecule in liquid form is kind of hydrogen bonding to about 3 other things around it. But what happens when it starts to crystallize is each water molecule can form longer hydrogen bonds, so they last longer, and it actually forms with 4 other water molecules, and so it starts to expand. Those crystals help it expand and become this perfect geometry, this hexagonal geometry that actually makes it less dense than liquid water. And this has really changed life on Earth. So, oops, let me go back. As you can kind of see what I'm talking about here. So this is liquid water. We have hydrogen bonds to 3 other, so we only have 3 other water molecules we're hydrogen bonded to. Whereas here, we actually end up having 4 other water molecules that we're hydrogen bonded to. So you get these hexagonal, so that means 6, you get these hexagonal structures, and you can see all of the stuff in here, all of our water molecules are actually more spread out than they are here, and that allows ice to float. Why is this important? Because if ice didn't float, all of the water below that would not be insulated and would eventually freeze. So if ice sank, it would basically cause this chain reaction of all of the water starting to freeze. Okay, everything would get really, really cold, all right, and that would cause problems. Another really important thing, especially for nutrition and life on Earth, is the fact that cold things sink. Okay, generally they will sink, and that actually helps uplift nutrient-dense water that's hanging out down there from all of the decay and dead stuff, and that really is super beneficial. That simple property of water that does seasonal turnover of lakes is also what powers something like El Nino and gives Peru its extremely rich fisheries, but we'll talk about that later. The other amazing thing about water, has an extremely high specific heat. This has to go back to the fact that it's polar. That polarity leads to hydrogen bonds. So what is specific heat? Basically, that is the amount of heat that can be absorbed to change a substance by 1 degree Celsius. So temperature, we need to remember, a lot of us kind of forget this. Temperature is actually just a way of measuring how much bumping around our molecules are doing, all right? So in order to kind of agitate water and make it starts bumping around and bumping into each other and starting to act all crazy, in order to do that, the first thing you need to do is break those hydrogen bonds. Luckily, those hydrogen bonds can absorb a lot of energy before they start to heat up, all right? Once again, high specific heat also means that it takes a lot to cool water down. So water is going to be highly resistant to temperature fluctuations simply due to those trillionths of a second hydrogen bonds. It's really incredible. And that's going to lead to very stable temperatures on planet Earth. So another thing is a high heat of vaporization. So this means that in order to basically turn water from a liquid to a vapor, you need to have a lot of energy. What's incredible about this is that a lot of life on Earth actually uses this tendency to cool off, because if you are breaking the bonds of that water and turning it into a gas and it's evaporating off of your body, that heat from your body that's causing that to happen is going to dissipate out into the atmosphere around you. So that heat energy is leaving your body and it's making you nice and cool. So we use that all the time. I want to go back really quick and talk about this, though. The specific heat of the high specific heat of water is also extremely important, because there's tons of chemical reactions happening in our bodies all the time, and that is going to lead to heat being released. And luckily, that heat is dissipating into water, and guess what? It's not really changing the temperature of our cells. If our cells weren't made of water, though, and those chemical reactions were happening, you basically cause a chain reaction and cells would constantly be exploding all the time, and then we'd have no life and we'd all be sad. All right? Talked about this. And I'm going to do a separate video really quick about pH, because it's kind of a dense topic and I want to make sure we have enough time. So this is it for now. Okay, that's it for today. Thanks a lot, guys. Stay curious. All right.